All right, thank you very much. It's really a full house today. Thank you for coming. So in this talk, we're going to talk about end-to-end encryption. And my name is Raphael, this is Konrad. I've been working on the MLS protocol since the beginning. I'm one of the co-authors of the protocol. And Konrad is one of the main contributors and also did his PhD about secure protocols and has been heavily involved also with an open source implementation of MLS. So we're going to start with a bit of an overview, like a historical overview of different end-to-end encrypted protocols, just to set the stage, to give you an idea why we need MLS now, why this whole thing was even developed. So this is a very coarse timeline of what happened in that space. It's very much oversimplified, of course. So I don't need to present PGP to this crowd, I'm sure. Email encryption, end-to-end encryption. I suspect quite a few of you still remember the off-the-record protocol, OTR, which was quite popular. The signal protocol also does not need an introduction anymore. And now we're talking about MLS. Let's look a little bit at the security properties that were added to these protocols over time. So if we start again with email end-to-end encryption, PGP, but they're derivatives of that, of course. What we had in terms of security properties was confidentiality, which essentially just means stuff is encrypted. You cannot decrypt it unless you know the secret key. And also authenticity, which means you know who encrypted something for you, and you also know to whom you encrypt something. So that's very much the baseline in terms of security properties for any kind of end-to-end encryption. The off-the-record protocol went a lot further by introducing much more fine-grained security properties. And we're going to go into them in detail later on. So this is just an overview at this point. Forward secrecy, you might have heard of that also in the context of transport encryption, TLS. Post-compromise security, it's a relatively new term for something that is not that new, but there is a very crisp academic definition of it now. Again, we're going to go into detail of what that means. Deniability has also been something that was introduced with OTR as a more concrete notion. And then, of course, what you know as the signal protocol these days, but initially that was called axolotl and then double ratchet. So what did that do? That essentially took all these relatively modern security properties from OTR and made them usable in asynchronous communication. So what that means is that OTR was a session-based protocol, if you recall the old days of Skype, where both sides had to be online at the same time for a message to go through. Then OTR would have been, the perfect protocol for this kind of sessions between two PCs, essentially. But these days we have smartphones, and they go offline a lot. So what we need is asynchronous communication where we don't have to rely on the other side to actually be online. We want the message to arrive as soon as the other side comes online, but the initial sending side could be offline. So this is essentially what the signal protocol did really, really well and brought the modern properties of OTR to smartphones. So what's missing? Because we already have a lot. What's missing is more versatility to cover more use cases in which end-to-end encryption could be used, particularly large group chats. So the current status quo is that end-to-end encryption works very well for one-to-one communication, but not so much for groups. They exist, of course. You've all been using group chats in end-to-end encrypted messengers, but they're essentially an abstract construction on top of one-to-one channels. It would also be nice to have a fully specified standard for end-to-end encryption. That was the case for OTR, but not so much for Signal. I mean, there's some documentation, but it doesn't have the level of a fully specified standard you can read and then just implement it and have something that is binary compatible with the Signal protocol. And also, it would be good to have open source implementations that are permissively licensed, and that can be used, in any kind of setting. So, going back to the scaling, and we're going to be talking about that a lot today. If we have a graph, and on one axis we sort of measure how well stuff scales, and on the other one how modern the security actually is, then we have email encryption at the lower left corner. We have client fan-out, like Signal, and like derivatives of the Signal protocol, like ORM from Matrix and Proteus from Wire, etc. Also, to some degree, iMessage. The security properties are much more modern, but it still doesn't scale very well. So, in order to make end-to-end encryption compatible for the masses, what popular apps like WhatsApp and Messenger and also different Matrix clients did was to use some sort of a trade-off where the security is still, a bit better, but not perfect. And it also scales a bit better, but it's also not perfect in terms of scaling. So what would be nice, of course, would be to have something that is, great in terms of security, but also scales really well. So a bunch of folks came together who all had the same thoughts about that. So a lot of, industry leaders, a lot of folks from academia, and so they, the industry folks brought a lot of experience. Academia, brought the precise knowledge that's necessary to actually build something secure, and that's essentially how MLS was born. Quickly going over functional properties. So we want things to be asynchronous, unlike the OTR protocol. That is important if you cater for smartphones, and you most probably do. We want group messaging to be supported, especially for larger groups, so that they scale well. We also want multi-device support. We no longer live in a world where everybody has at most one desktop PC at home. We all have several devices these days. We want a protocol to be extensible so that it can be adapted to different use cases. It should also be able, to degree at least, to support federation and decentralization, at least to the degree that it wouldn't stand in the way of that. And last but not least, it really needs to be usable. So it's no good if we just construct something that academically is great, looks fantastic on paper, but then you cannot use it because it forces users to adopt a new user experience they're not used to at all. So going back to the MLS security properties, we start with what OTR and Signal introduced, and then we try to go a bit beyond it. So confidentiality and authentication, just like PGP, that's the baseline. Forward secrecy, post-compromise security, we'll get to that in the next slide, I think. But also, it would be good to have something that really caters for groups and introduces something new. Sounds a bit clunky, agreement on group state. What that means is that every member of a group chat, if you will, has the same view on the list of members, for example, than everybody else. That sounds very trivial, but that's not the case typically for Signal or Matrix or others. There's no cryptographic guarantee that you actually see the same people in the room. And then one more rather informal property, which I say informal because it's not really a property of the protocol as such, but if you use a server to relay messages that behaves honestly, you can also have something that is very close to transcript consistency. And what that means is that when somebody sends out a message, everybody sees the same message, and a malicious insider cannot trick people into seeing different messages. Why do I mention that? That's again not the case with a protocol like Signal or OTR, where you can effectively send different messages in a group without the server being able to detect that and without users being able to detect it. So finally, getting back to forward secrecy and post-compromise security, what does that mean? So with end-to-end encryption, in the context of messaging, we have really, really long sessions, as opposed to TLS, where you have really short sessions of maybe seconds or minutes, at most hours. Here we could have years between two users. Same as with PGP. And with PGP, if your key leaks, your encryption key, that is a bit of a problem, because then the attacker can decrypt potentially years worth of past messages. And also, if the compromise is not detected, as it's often the case, you can also stealthily decrypt going forward. So we sort of have to assume that stuff can leak if we look at years. So, and we need to fix the protocol here so that the blast radius of such an endpoint compromise is not too big. And that gives us these two properties. Like forward secrecy means that even if there is a compromise, you cannot really go back all the way in time. You can only go back to a certain extent. And then there's post-compromise security, which is now just the temporal opposite of that, meaning when the compromise is over, like the key has leaked, but there is no long-term compromise of a device, then actually the device should be able to heal itself. And that property is a lot harder to tackle because you need to come up with new key material and you need to send that to everybody in a group, to whoever you're messaging with. So you could say that MLS is really great when it comes to post-compromise security, PCS. It makes it so that it actually scales well compared to other protocols. And because that's such an important thing, we made that a sticker. You can find them all across the venue. Maybe you've seen them already. And finally, so with all this sort of wish list, how do we cook up a protocol? What happened there? It all started with something called asynchronous ratcheting trees. And the idea there was to use a binary tree to model group messaging and make that much more efficient. So that was an initial idea, and then it was refined over time. The whole thing was brought to IETF as a standardization body, which was a good pick as a forum to get both industry and academia together. And the idea was also that we sort of mimic what TLS 1.3 did in terms of how the development process was approached. The IETF works with draft documents, and intermediary drafts were then given to academia for analysis, and which is good because then you get some feedback, and you should actually also listen to the feedback, which is even better. So we went through multiple iterations there. So you could say we really worked hand in hand with academia, and that's how you should actually design a modern security protocol. All right, that was it for the introduction, and now hand it over to Konrad, who's going to talk a bit more about the details.
Okay, so I want to talk a bit about how MLS achieves the scalability that Raphael has talked about. But before I start with that, I want to talk a bit how MLS slots into your architecture and the ecosystem a bit more broadly. And we start with a protocol that most of you are familiar with, TLS. And TLS slots quite nicely between a transport layer, TCP UDP, or UDP if you want to use DTLS, and the application layer where you have your HTTP, SMTP protocol, what have you. And then in between you can slot in TLS if you want to secure your plain text on the wire. And the traffic is going to be authenticated using an X509 certificate, which in turn is authenticated using some sort of public key infrastructure. And MLS is quite similar to that. It also slots into the stack, this time between the transport encryption, and if you want, you can have additional layers on top of that. So for example, it could be TLS and then HTTP, and then you can slot in MLS. MLS in turn is authenticated using credentials, which are in turn authenticated using an authentication service, which I'll talk about in a minute. And then on top of MLS, you can send your application messages. And in contrast to TLS, MLS, of course, doesn't just protect the messages on the wire, but in an end-to-end fashion. So in terms of architecture, MLS requires two additional services. One of them I've already just mentioned, the authentication service, and the other one is the delivery service. The authentication service is there to authenticate the credentials, which are each individual MLS client uses to sign MLS messages and authenticate them to other MLS clients. And these services are less, if you think of service, you can think of a server that's running somewhere on the network and it's doing things. But in this case, the service is more of an abstract thing, where parts of the service could also be on the client. So for example, for the authentication service, this could be much like Signal, where you just have public keys, and the only way you authenticate them or you verify them is by scanning a QR code on the phone of your contact. On the other hand, it could also be much more infrastructure-heavy thing. You could use X509 certificates and a PKI with CAs and all the bells and whistles. So both things work with MLS. MLS doesn't really care much what the credential actually looks like. And then on the other hand, there's the delivery service, and the job of the delivery service is, of course, to deliver messages, but more crucially, to ensure that all MLS clients involved in a specific group agree on the order of the messages that they receive. And again, this could be a client-side thing where you have some sort of distributed algorithm that allows the clients to agree on the order of agree on the order in which they receive the messages. Or it could be a server that's just in the middle of everyone and that takes the message as they come and ensures that everyone distributes them in a ensures that everyone gets them in a specific order. Okay, so now let's see how MLS actually achieves this scaling properties. And again, we start with a baseline where we construct. We don't look at MLS yet. We look at a group messaging protocol that's built naively out of one-to-one channels, for example, signal channels. And this is going to be a bit simplified, right? I'm not going to go too much into the details in the interest of time, but it looks roughly like that. As Raphael just mentioned, if Alice wants to update her, achieve post-compromise security, recover from a compromise, what she needs to do is update her key material. And so she updates her key material, and then she needs to send the updates to all of the other group members, in this case Bob, Charlie, and Dave. And because these are one-to-one channels, Alice needs to send the update n times, where n is the number of members in the group. So this causes n encryption operations and n times the ciphertext upload. So if we look at MLS, MLS also has the participants in the bottom row, just like in the previous case, but it also has the support structure of additional public keys on top, such that they form a binary tree. And these public keys that we have in addition to the public keys of the individual members allow us to achieve these scaling properties. So if Alice, sorry, I should go back, and one crucial property of this tree is that each participant in the leaf knows the private key material to all the public keys in the nodes from the leaf of the participant to the root of the tree. And so if Alice wants to update her key material, she doesn't have to send the updates to, or encrypt the updates to Bob, Charlie, and Dave individually, and instead she can encrypt the message to the to some of these intermediary nodes in the tree. So in the case of Bob, she has to send it to Bob directly, but in the case of Charlie and Dave, she can actually send the update or encrypt the update to the root of the subtree in which Charlie and Dave are. And you can imagine if we have a much bigger tree, then the effect is quite a bit more pronounced. Okay, so with that in mind, let's look at a slightly bigger example. This is, of course, a bit exaggerated, but this is kind of just to show what this looks like. With this one-to-one based group messaging, you have a linear increase in the overhead that you get in terms of encryption operations and upload of ciphertexts. So if you have a group with 100,000 members, you have 100,000 encryption operations and ciphertext uploads each time you want to update your key material. If you use something like MLS, where you have this nice binary tree structure, it scales logarithmically, and so you end up with just 17 operations. Of course, this is a bit exaggerated, so let's look at a slightly more realistic example. But in this case, let's make it a bit more interesting if we want to use a post-quantum secure cipher suite. So we have a slightly more realistic group size, let's say 1,000. And let's say we want to use the freshly standardized Kyber 768 algorithm to encrypt our key material as a key encapsulation mechanism. And the ciphertext size for Kyber is about 1 kilobyte. So group size 1000, 1 kilobyte update size. So if you have this group based on one-to-one channels, you have a linear fan-out payload size, and that is 1 megabyte to upload for each update for the participant. That sounds doable, but then if you imagine a group of 1,000 people and everyone does an update, then you also have to download all the updates from the other participants, and you end up with a gigabyte of download if everyone does an update once. And then if you want somewhat frequent updates, say everyone updates their key material once a week, you end up with a gigabyte per week, and if you imagine that on a smartphone with a media connection, it's no fun. And then if you use MLS, in contrast, you still have to, it's still relatively expensive in terms of a wireless connection, so it's 10 kilobyte to upload for an update, but it's only 10 megabytes to download for each group member if everyone does an update. So it's still not great, but it's a lot more bearable than a gigabyte. Okay, let's go back to MLS and the tree. And MLS supports a number of operations. And clearly we need the basic operations. You need to remove group members, you need to add group members, you need to update the key material, as you've just seen, how it roughly works in the tree. And then you need to send application messages. And the application messages are essentially just encrypted using, you can think of it as using the key on the top of the tree that everyone knows. And if we look at a remove operation, so let's say Alice wants to remove or has removed Charlie, then what happens is that the nodes in the tree to which Charlie knows the key material need to be removed from the tree to ensure that Charlie doesn't really, cannot read messages in the future anymore, right? This is another instance where we actually need post-compromise security, not just in an adversarial scenario, but just in a basic group operation scenario. And so when we blank these nodes, that of course also means there are no public keys anymore, and in this way, unfortunately, the efficiency of the whole thing suffers a bit. I'm not going to go into detail on how this affects exactly how you encrypt the updates, but you can think of it as like the fewer of these intermediary nodes you have, the less efficient the group becomes. Luckily, these blanked nodes fill up again once someone, like in this case, for example, if Dave updated his key material, the node would be filled again with a new public key. And then if we wanted to add someone, the added participant, Edith, would be fitted in the first empty leaf, or indeed, if all the leaves are full, the tree would just be extended to the right, and you have, again, a full binary tree, with most of the leaves being blank, but again, that fills up as soon as the newly added people do update operations. And then I pass it back to Raphael.
Thank you. Yeah, so now that you know everything about MLS, what's next? So I mentioned implementations earlier, and that's crucial if we want people to use MLS. Currently, we have implementations in Rust and in C++ that are compatible with the RFC that came out in June or July this year. We have been involved with one that is called OpenMLS. It's written in Rust. It's permissively licensed under the MIT license. And the idea behind that was, on one hand, that it started very early alongside the development of the protocol, just to check that stuff actually works. And these days, the idea behind it is that it is some sort of a community project that is as useful as possible to as many projects as possible. And we've received quite a bit of code contributions already, and it's being used and tested in different applications. At the same time, there's more that is in the works. I think there's a Java implementation, a Go one, a Ruby one, an F-star one, for those who are familiar with that. So we think that at some point there will be several implementations you can pick from. What else? So the RFC is there. And the MLS working group at the IETF is currently working on extensions to the protocol. So we already talked about post-quantum resistance. That was the one of the first extensions that was added. We are also looking at more efficient multi-device support, which you can already do with MLS as it is, but there are things you can still optimize. And we are also looking into other security properties that are not necessarily important in the general setting, but for more specific applications, like, for example, deniability, but there are also other things that we're looking at. So there is some ongoing work, essentially, beyond this baseline that we now have with MLS. There's also a new IETF working group that recently emerged that is called MIMI, More Instant Messaging Interop, on the backdrop of the European Digital Markets Act that incentivizes different messengers to become interoperable. And so the idea behind that working group is to standardize some of the technology for that, and MLS is one of the building blocks, specifically for the encryption, obviously. We've also been working, and by we I mean Conrad and I, at Phoenix R&D, on trying to see how we can build privacy-preserving architecture for MLS. So obviously, with large groups, MLS is super useful for corporate messaging, because that's why you tend to have a lot of large groups. But not only, we think that it would be nice if we can embed the whole thing in an architecture that really gives you, a reasonable degree of metadata protection, etc. So this is ongoing work and not part of this talk, but it's something that's coming up. So where can you actually see MLS or experience MLS already? WebEx from Cisco was the first large deployment of MLS, and actually they deployed a version that was pre-RFC. So if you've been using WebEx, there's an option to enable end-to-end encryption, and that is using MLS. So that was a really nice test at scale to see how well MLS works. And then also, quickly after the RFC was published, Google committed to using MLS going forward for Google Messages and RCS, which is this successor of SMS and MMS, for those who have never heard the term. So this is nice, because that means there might be very large deployments. We know that other large messengers are testing it currently, but these things tend to be A, relatively secretive, and B, move slowly, but there might be some news at some point. All right, that's the end of the talk, and so we'll be taking some questions after that. If you want to contact us, there's an email address. You can also call our colleague Julian on a decked phone, and don't forget about the stickers. Thank you very much.
Yes, don't forget about the stickers. Very good call to action. Okay, thank you very much for your presentation. So there's a bit of time for questions. Line up at the microphones, and there will be a bit of a bias for the internet because they cannot be here. So we start off with the Signal Angel, please.
What is the current state of adoption by Matrix or XMPP?
Matrix has been looking into it. I think they even have a dedicated website for that is called arewemlsyet.com. And so that's where they publish updates. And with XMPP, there were talks. I don't know how far along that is.
Okay, microphone one.
Yes, thank you for your talk. In one of your slides, you mentioned that you took inspiration from the way they did it in TLS 1.3. And I'm a bit curious what that means and what you have done to overcome the hurdles with the flexibility and things with the protocols such as TLS.
Do you want to take that one?
Yeah, I mean, so I think the first thing that was inspired by TLS is just procedurally. It was also an IETF protocol. A good few people who were involved in the in the TLS standardization were also involved in the MLS one. Also, TLS 1.3 has been a success story, as Raphael mentioned, in terms of how industry and academia have collaborated and how there's been a back and forth, how academia has analyzed protocol drafts, and that has influenced the whole protocol design and the security, of course. So that was one thing, how it's in one way in which it's inspired. And where MLS uses on a technical level, MLS uses the TLS presentation language, the serialization, for example. We're also, and also the credentials. It does support X509, so in that way it's somewhat compatible. I guess you could emulate TLS 1.3 using MLS as a one-to-one connection, but I think that's where the similarity ends. I don't know, Raphael, if you want to.
Yeah, I think that covers it pretty much.
We had the benefit of not having these backwards compatibility issues, so we had to pass through middle boxes and all that stuff, so we're lucky in that.
Yeah, I guess it's important. Yeah, this is about TLS 1.3 and not the older versions, obviously.
Yeah,
that were highly problematic for different reasons.
Okay, thank you.
Thanks.
Okay, is there another question from the internet?
Yes, isn't the wire communicator actually a proper and compliant implementation of the MLS standard?
You mean the wire messenger? I think they committed to using MLS in the future. I don't think it has been fully rolled out yet. I mean, historically, I worked there for full disclosure. Wire has been using Proteus, which is very similar to the Signal protocol. Yeah.
Okay, microphone 2, please.
Yeah, thanks for the talk. You talked a bit about sending key updates. How would Alice, for example, authenticate herself after her key leak? Like, authenticate the key update messages? How would that work?
That's a good question. MLS kind of punts a lot of the authentication stuff to the application or to the layer above, if you will. That's on the one hand, it's just so it's more modular, but on the other hand, it also means that it's hard to answer that question. It really depends on how the application chooses to manage authentication key material. So, for example, what you could do in a similar way that MLS rotates, or you do these encryption key updates using MLS, you could also do authentication key updates and refresh your authentication key. I mean, that leads to other operational questions, but that's kind of independent from MLS. The authentication key management.
But yeah, what's within MLS, of course, is signatures. So MLS uses signatures to authenticate messages, but the management of the signature keys is out of the scope.
Thanks.
Okay, how's internet doing?
Yes, do you know any implementations of MLS in Python or other languages? And do you encourage people to start implementing them?
So I'm not aware of any implementation in Python. I mean, of course, people, should implement that if they're up for it. It's always good to have, different implementations. That being said, it's also great to have really mature implementations. So, as you know, with security protocols, it's great if they're audited and have stood the test of time for a bit before you deploy them. But yeah, so what I showed on one of the slides is what I'm aware of at this point. That was Java, Go, Ruby. I think that's it.
And if anyone wants to implement MLS in Python or has implemented it, we have an active interoperability dialogue. Just send an email to the mailing list. Multiple groups are coordinating how to exchange test vectors. We have a whole, what's it called? A harness, like an interoperability harness, where you can plug in different implementations and test how they interoperate and stuff. So if there's anyone who wants to do that, just come talk to us.
Okay, microphone 4, please.
Yeah, thanks for the talk. In the slide about fanout in MLS, you said that the PCS updates would send to some to the lowest common nodes in the tree.
Yeah.
Why not just send the PCS update to the root of the tree?
That's a good question. If you look at the threat model for post-compromise security with these state snapshot compromises, then you have to assume that the adversary, so if Alice is compromised and Alice knows all the secret key material up to the root, including the root, then the adversary also knows this key material. So if Alice encrypts the new key to the key in the root, then the adversary can just decrypt it. So Alice needs to encrypt the key to the keys that Alice herself doesn't really know or didn't know. So it needs to be off of Alice's path. It's what we call the co-path.
Okay.
But yeah, that would make life a lot easier, but unfortunately, it doesn't quite work.
Thank you.
Okay, microphone 1, please.
Thank you for your great work. I have one question about PCS. You mentioned that there's this event of the compromised key material. Is it that the rotation is only triggered when there's a known event of compromisation? Or is it like automatically done regularly? And is this the frequency, is it bound to the implementation of the client? Or is it built into protocol? And if yes, how often is the rotation done? So basically, how long is the forward secrecy ensured, basically, after the compromise event?
So, the assumption is that you cannot always detect a compromise. So the result from that is you should do it automatically. And that is entirely up to the application in that sense. Like the protocol just offers the possibility to do it. But beyond that, the applications should define some policy how frequently that should be done. And that will depend a lot on the constraints of the clients, in what environment that is being deployed, etc. How much bandwidth that's going to consume. So you can sort of, fine-tune it and find a trade-off that works for you. Of course, from a security perspective, the more often you do it, the better.
Is there kind of a best practice or some kind of guidance that you give to implementations? Like, is it done hourly, daily, weekly, monthly? So what can we expect typically?
There is another protocol in the working group called the architecture document, and I think there is a little bit of guidance, in there. But ultimately, it's hard to, to give good advice in that sense, because it really depends on what you want to achieve. For some applications, it's great to do it hourly. For others, it might be good enough to do it weekly. It's hard to come up with a general rule of thumb here.
Okay, thank you.
And I mean, you're free to scale it however you want, right? So if you have a big group where updates are expensive, then you say, okay, it's a big group, so it's very possible that the content might leak in some other way. It's a lot of compromise surface, so it might not be worth updating that frequently. Also because it's expensive, and in smaller groups where you have maybe more secretive conversations, I don't know, then you might update more regularly. Yeah, it's up to you essentially.
Thank you.
Okay, another question from the internet, please.
How is MLS collision resistant if multiple key updates are sent at the same time?
That's a very good question. So, in general, these control messages like update, add, remove, etc., they have to happen in a certain order that is the same order for everybody in an MLS group. And this is the duty of the delivery service to ensure this ordering, essentially. So the delivery service has to either do that in real time, and then, if two members send an update at the same time, then there's one winner, one loser. Or if there is no delivery service that can do that in real time, you need to apply some logic to come to the same ordering, offline, asynchronously, so that stuff is being applied. And obviously, then you still need to discard some of the messages. So it boils down to one of the hard problems of distributed systems that MLS doesn't solve, obviously.
Okay, last quick and concise question from microphone 2, please.
Hi, do you have any interesting insight or an opinion about the recent revelations about push messages that went through Google and Apple and they turned out to be passed through to intelligence agencies?
Yeah, well, we were involved with that. There's no direct connection to MLS, however. So happy to talk about it. It's probably the wrong stage for it. But thanks for bringing it up.
Okay, this concludes this session. Thanks again, Konrad and Raphael.